Hello, and welcome to the introductory lesson of the Apache Cassandra course offered by Simplilearn. This lesson will give you an overview of the course, its prerequisites, and the value it will offer you. Before you start, please spend some time and go through the key features of Simplilearn offerings displayed on the screen. After completing this course, you will be able to describe the need for big data and NoSQL, and explain the fundamental concepts of Cassandra. You will also be able to describe the architecture of Cassandra and demonstrate data model creation in Cassandra. Finally, you will be able to use Cassandra database interfaces and demonstrate Cassandra database configuration. The Apache Cassandra training course offered by Simplilearn provides details on the fundamentals of big data and NoSQL databases. The course will also provide an overview of Cassandra and its features. Further, it will enhance your knowledge on the architecture and data model of Cassandra and provide an overview of the installation, configuration, and monitoring of Cassandra. Finally, the course will enhance your knowledge on the Hadoop ecosystem of products around Cassandra. The course is aimed at professionals aspiring for a career in NoSQL databases and Cassandra. Analytics professionals, research professionals, IT developers, testers, and project managers are the key beneficiaries of this course. Other aspirants and students who wish to gain a thorough understanding of Apache Cassandra can also benefit from this course. Fundamental knowledge of any programming language is a prerequisite for the course. Participants are expected to have basic understanding of any database, SQL, and query language for databases. A working knowledge of Linux or Unix-based systems is an added advantage for this course, although it is not mandatory. The Apache Cassandra professionals will be able to demonstrate their expertise in the fast-growing big data industry, well-placed to benefit from the growing demand in NoSQL databases, able to benefit from the shortage of Cassandra-trained professionals, well-equipped to take their organization towards big data analytics using Cassandra, experienced in tools used to process huge amounts of data, in the forefront of the big data technology, which is expected to be in demand for the next 10 years. There are 8 core lessons in this course, apart from the current lesson. Course Overview. Take a look at the course map displayed on the screen. In addition to the lessons, there are some demos provided in the course to facilitate a better understanding of the concepts. This concludes the course overview. The next lesson provides an overview to big data and NoSQL. All the best! Hello and welcome to the first lesson of the Apache Cassandra course offered by Simplilearn. This lesson will provide an overview of the big data and NoSQL database. The Apache Cassandra course by Simplilearn is divided into 8 lessons as listed. This is the first lesson, Overview of the Big Data and NoSQL Database. After completing this lesson, you will be able to describe the 3 V's of big data. You will also be able to discuss some use cases of big data. Further, you will be able to explain Apache Hadoop and the concept of NoSQL. Finally, you will be able to describe various types of NoSQL databases. Big data has 3 main characteristics: volume, velocity, and variety. Volume denotes the huge scaling of data, ranging from terabytes to zettabytes. Velocity accounts for the streaming of data and the movement of large volumes of data at high speed. Variety refers to managing the complexity of data in different structures, ranging from relational data to logs and raw text. In addition, there are other V's of big data. However, they're not as popular. These are veracity, visualization, and value. Veracity refers to the truthfulness of data. Visualization refers to the presentation of data in a graphical format. And value refers to the derived value of an organization from using big data. The term volume refers to data volume, which is the size of digital data. The impact of Internet and social media has resulted in the explosion of digital data. Data has grown from gigabytes to terabytes, petabytes, exabytes, and zettabytes. As illustrated on the image, in 2008, the total data on the Internet was 8 exabytes. It exploded to 150 exabytes by 2011. It reached 670 exabytes in 2013. It is expected to exceed 7 zettabytes in the next 10 years. The table contains various terms used to represent data sizes. The size, along with the power and description of each data term, is given. It is recommended you spend some time to go through the contents of the table for better understanding. The new terms added to address big data sizes are exabyte, zettabyte, and yottabytes. Typically, the term big data refers to data sizes in terms of terabytes or more. The term velocity refers to the speed at which the data grows. People use devices that create data constantly. Data is created from different sources, such as desktops, laptops, mobile phones, tablets, and sensors. Due to the increase in the global customer base and transactions and interactions with customers, the data created within an organization is growing along with external data. As illustrated on the image, there are many contributors to this data growth, such as web, online billing systems, ERP implementations, machine data, network elements, and social media. Growth in revenues of organizations indicate growth in data. The term variety refers to different types of data. Data includes text, images, audio, video, XML, and HTML. There are 3 types of data. Structured data, where the data is represented in a tabular format. For example, MySQL databases. Semi-structured data, where the data does not have a formal data model. For example, XML files. Unstructured data, where there is no predefined data model. Everything is defined at runtime. For example, text files. Digital data has evolved over 30 years, starting with unstructured data. Initially, the data was created as plain text documents. Next, files were created, and data and spreadsheets increased the usage of digital computers. The introduction of relational databases revolutionized structured data, as many organizations used it to create large amounts of structured data. Next, the data expanded to data warehouses and storage area networks, or SANs, to handle large volumes of structured data. Then the concept of metadata was introduced to describe structured and semi-structured data. Big data has the following features. It is extremely fragmented due to the variety of data. It does not provide decisions directly, however, it can be used to make decisions. Big data does not include unstructured data only. It also includes structured data that extends and complements unstructured data. However, big data is not a substitute for structured data. Since most of the information on the Internet is available to anyone, it can be misused by antisocial elements. Generally, big data is wide. Therefore, you may have hundreds of fields in each line of your data. It is also dynamic, as gigabytes and terabytes of data is created every day. Big data can be both internal, generated within the organization, and external, generated on social media. Every industry has some use for big data. Some of the big data use cases are as follows. In the retail sector, big data is used extensively for affinity detection and performing market analysis. Credit card companies can detect fraudulent purchases quickly so they can alert customers. While giving loans, banks examine the private and public data of a customer to minimize risk. In medical diagnostics, doctors can diagnose a patient's illness based on symptoms instead of intuition. Digital marketers need to process huge customer data to find effective marketing channels. Insurance companies use big data to minimize insurance risks. An individual's driving data can be captured automatically and sent to the insurance companies to calculate premium for risky drivers. Manufacturing units and oil rigs have sensors that generate gigabits of data every day, which are analyzed to reduce risk of equipment failures. Advertisers use demographic data to identify the target audience. Terabytes and petabytes of data are analyzed in the field of genetics to design new models. Power grids analyze large amounts of historical and weather forecasting data to forecast power consumption. With the origin of big data analytics, you can use complete sets of data instead of sample data to conduct an analysis. As represented on the image, in traditional analytics method, analysts take a representative data sample to perform analysis and draw conclusions. Using big data analytics, the entire dataset can be used. Big data analytics help you find associations in data, predict future outcomes, and perform prescriptive analysis. The outcome of prescriptive analysis will be a definitive answer, not a probable answer. Further, using big data for analysis also helps in taking data-driven decisions instead of decisions based on intuitions. It also helps organizations increase their safety standards, reduce maintenance costs, and prevent failures. Traditional technology can be compared with big data technology in the following ways. Traditional technology has a limit on scalability, whereas big data technology is highly scalable. Traditional technology uses highly parallel processors on a single machine, whereas big data technology uses distributed processing with multiple machines. Further, in traditional technology, processors may be distributed with data in one place. However, in big data technology, the data is distributed to multiple machines. Traditional technology depends on high-end, expensive hardware, costing more than $40,000 per terabyte. On the other hand, big data technology leverages commodity hardware, which may cost less than $5,000 per terabyte. Traditional technology uses storage technologies, such as SAN, whereas big data technology uses distributed data with data redundancy. Apache Hadoop is the most popular framework for big data processing. Hadoop has two core components: Hadoop Distributed File System, or HDFS, and MapReduce. Hadoop uses HDFS to distribute the data into multiple machines. It uses MapReduce to distribute the process to multiple machines. Further, Hadoop distributes the processing action to where the data is, instead of moving data towards the processing. The concept of distribution performed by HDFS and MapReduce is illustrated on the image. First, HDFS divides the data into multiple sets, such as Data 1, Data 2, and Data 3. Next, these datasets are distributed to multiple machines, such as CPU 1, CPU 2, and CPU 3. This action is performed by MapReduce. In the end, the processing is done by the CPUs of each machine on the data assigned to that machine. HDFS is the storage component of Hadoop, which stores each file as blocks with a default block size of 64 megabytes. This is larger than the block size on Windows, which is 1K or 4K. HDFS is a write-once, read-many form of file system, also called worm. Blocks are replicated across nodes in the cluster. HDFS provides 3 default replication copies. The image illustrates this concept with an example. Suppose you store a 320 megabyte file into HDFS. It will be divided into 5 blocks, each of size 64 megabytes, as 64 multiplied by 5 is 320. If there are 5 nodes in the cluster, each block is replicated to make 3 copies to result in a total of 15 blocks. These blocks are further distributed to the 5 nodes so that no 2 replicas of the same block are on the same node. MapReduce is the processing framework of Hadoop. It provides highly fault-tolerant distributed processing of the data distributed by HDFS. MapReduce consists of 2 types of tasks, mappers and reducers. Mappers are tasks that run in parallel on different nodes of the cluster to process the data blocks. In programming language, mappers are called key-value pairs. After completion of the map tasks, results are gathered and aggregated by the reduce tasks of MapReduce. Reduce tasks consolidate and summarize the results. Each mapper runs on the machine on which the data block is assigned. Data locality is preferred. This follows the principle of taking processing to the data. NoSQL is the common term used for all databases that do not follow the traditional Relational Database Management System, or RDBMS principles. In NoSQL databases, the overhead of the ACID principles is reduced. ACID stands for atomicity, consistency, isolation, and durability. This is a set of properties that guarantee the reliable processing of database transactions. These principles are guaranteed by most RDBMS. The process of normalization is not mandatory. With big data, it is difficult to follow RDBMS principles and normalization. NoSQL databases prefer denormalized databases. Due to the transactional database requirement of RDBMS, the relational databases are not able to handle terabytes and petabytes of data. A NoSQL database is used to overcome the limitations of transactional databases. The image represents people uploading the data and reading the data from a transactional database. Eric Brewer, a computer scientist, proposed the Brewer's consistency, availability, and partition tolerance, or CAP principle in 1999. CAP is the basis for many NoSQL databases. In a distributed system, consistency means that all nodes in the cluster view the same data at the same time. Availability means that a response is guaranteed for every request received. The response can be in terms of whether a request was successful or it failed. Partition tolerance means the system continues to operate despite the ad hoc message loss or failure on part of the system. Further, Brewer stated that it is not possible to guarantee all 3 aspects simultaneously in a distributed system. Therefore, most NoSQL databases compromise on one of the 3 aspects to provide better performance. There are 4 main types of NoSQL approaches: graph database, document database, key-value stores, and column stores. Let us discuss each of these one by one. First is the graph database. A graph database helps in representing graphical data in the nodes and edges format. Some of its features are as follows. Graph databases can handle millions of nodes and edges. They can perform efficient depth-first and breadth-first searches on the graph data, other graph searches, and traversal algorithms. Neo4j and FlockDB are the popular graph databases. The image depicts a graph with 4 nodes in a Neo4j database. Second is the document database. A document database helps in storing and processing a huge number of documents. In the document database, you can store millions of documents and process fields. For example, you can store your employee details and their resumes as documents, and search for a potential employee using fields like the phone number. MongoDB and CouchDB are the popular document databases. The image depicts the fields of a document stored in MongoDB. Third is the key-value stores. These store the data in key and value formats, where each piece of data is identified by a key and has associated values. In the key-value stores, you can store billions of records efficiently and provide fast writes as well as searches of data based on keys. Cassandra and Redis are popular key value stores. The image depicts the keys and values stored in a Cassandra database. You will learn more about key value stores when we discuss Cassandra in the upcoming lessons. Last is the column stores. These are also called column-oriented databases. Column stores organize data in groups of columns and are efficient in data storage and retrieval based on keys. Some of their features are: HBase is part of the Hadoop ecosystem that runs on top of HDFS to store and process terabytes and petabytes of data efficiently. Column stores normally maintain a version of the data along with each value of data. HBase and Hypertable are the most common column stores. The image illustrates how HBase stores the data. Data is organized by column families, and each column family can have one or more columns. For each column, along with the data value, a version number indicating the time of data update is also stored. The column-based data is stored along with the key. Note that NoSQL databases cannot replace general-purpose databases. Although they provide better performance and scalability, they compromise on some aspects like ease of use and full SQL query support. Let us summarize what we have learned in this lesson. Big data is mainly characterized by variety, velocity, and volume. With the origin of big data analytics, complete sets of data can be used to conduct an analysis instead of sample data. Apache Hadoop is the most popular framework for big data processing. It has two components, HDFS and MapReduce. HDFS is the storage component of Hadoop, and MapReduce is the processing framework of Hadoop. NoSQL is the common term used for all the databases that do not follow traditional RDBMS principles. It is based on Brewer's CAP principle. Brewer stated that it is not possible to guarantee the consistency, availability, and partition tolerance aspects simultaneously in a distributed system. This concludes the lesson on overview of big data and NoSQL. The next lesson will provide an introduction to Cassandra. Hello and welcome to Lesson 2 of the Apache Cassandra course offered by Simplilearn. This lesson will provide an introduction to Cassandra. Simplilearn's Apache Cassandra course is divided into 8 lessons as listed on the screen. Introduction to Cassandra is the second lesson. By the end of this lesson, you will be able to describe Cassandra and its features, describe when Cassandra is used, demonstrate how to work with the command line interface of Cassandra, list the advantages and limitations of Cassandra, and demonstrate how to install a VMware player. Cassandra is a NoSQL database that is highly scalable and big data ready. You learned in Lesson 1 that a NoSQL database is one that can work with denormalized data. Cassandra is a distributed database that is highly fault-tolerant with no single point of failure. Further, it is a high-performance database. Cassandra derives its name from Greek mythology. Cassandra was the daughter of King Priam of Troy and his wife Hecuba. Cassandra had the power to predict the future, but she also had a curse that nobody would believe her predictions. True to its name, the Cassandra database holds a lot of promise for the future, but suffers from many limitations as well. Cassandra was initially developed in 2008 at Facebook as a combination of the Big Table data store used by Google and the Dynamo data store used by Amazon. It was developed by Avinash Lakshman, the author of Amazon Dynamo, and Prashant Malik. It was developed to solve the inbox search problem of Facebook. It has evolved a lot since its inception in 2008. It started with the concept of column families and supercolumn families, but later evolved as a key value store. You can still get messages from Cassandra about column families. Version 1.0 was released in 2011. In 2014, Cassandra became an Apache open source project, and the current version 2.0 was released. The following are the main features of Cassandra. Cassandra is a key-value database. Data is stored as tables and columns, and every table has a primary key. Further, Cassandra has a limited SQL interface. In addition, it provides very fast read and writes. A sample Cassandra query is provided on screen. Select ticker, comma value from stocks where ticker is equal to XYZ order by ticker. Observe that the syntax is similar to that of a SQL in a relational database management system. Cassandra is used to store a huge amount of information very quickly. For example, when you are processing telecom switch data or stock market data, a huge volume of data is generated every minute. Cassandra is also useful when you want full indexed search to get the data quickly, and the data needs to be sorted in a predetermined order. Full indexed search is search performed using a key. Another case where Cassandra is useful is when you expect an upsurge in data size. Cassandra enables scaling by adding more nodes as the data grows. You can also use Cassandra when you want a highly fault-tolerant cluster with no single point of failure. It is also preferred when you need high performance for both data read and write. An example of a simple Cassandra program is provided on screen. In this example, you create a table, insert a few records, and fetch data from the table. You can see that the Cassandra syntax is very similar to the standard SQL syntax. The example creates the table called stocks with 2 columns, inserts 3 rows into this table, and selects data from the table for a particular key. Observe that Cassandra uses the primary key of the table to fetch the data. The data is also stored in the primary key order. Cassandra provides a command line interface that is similar to the Linux shell. It can be invoked with CQLSH if that is in your path, or using bin/CQLSH from the Cassandra base directory. You can use CQLSH --h to get help and arguments for the command. Before starting CQLSH, you need to set the all uppercase CQLSH _host parameter to the address of one of the hosts where Cassandra is running. Within CQLSH, you can access the history of commands with the up arrow. Most commands have elaborate help available, and you can access it using the help command within Cassandra. You can exit the shell using the exit command. Note that you need to terminate each command with a semicolon. The image shows how to run CQLSH and also depicts the sample output from CQLSH. Cassandra has many advantages for processing big data. It is highly fault-tolerant with no single point of failure. This means that if any node in the cluster fails, other nodes will take over and complete the work. Every node in the cluster is identical, as there are no masters or slaves in Cassandra. Therefore, one machine cannot become the bottleneck in the system. Further, you can add a machine to the cluster or remove a machine from the cluster anytime without downtime. Cassandra also provides very fast data writes, allowing real-time processing of big data. Cassandra outperforms many other NoSQL databases in terms of many performance benchmarks. Cassandra is not a general-purpose database due to some limitations. First, it doesn't provide aggregation of data with group by sum, min, or max like relational databases. Any aggregation has to be pre-computed and stored. Second, there are no joins of tables, so data has to be denormalized before getting stored in Cassandra. Third, it doesn't support additional search clauses or conditions. Only keys or indexes can be used for search. We will talk more about this restriction later in the course. Lastly, there is no sorting provided on non-key fields. In a later lesson, you will learn to install Cassandra on a Ubuntu Linux system. However, if you need to work on an operating system other than Linux, you can access the software provided by VMware. This software allows running one operating system on another using a virtual machine. This is facilitated by VMware Player. For non-commercial use, VM Player can be downloaded and used free of cost from the VMware website. Simplilearn has created a virtual machine on VMware Player. This machine, known as Hadoop Pseudo Server, comes with the pre-installed Ubuntu 12.04 LTS operating system and Hadoop setup. It can be opened with the VMware player and can be used for installing Cassandra. Hadoop pseudo server can be downloaded from the given link. PuTTY is a popular free tool for connecting to Linux systems from Windows through a remote terminal. It overcomes some of the limitations of the VM. For example, it allows moving the mouse pointer with ease, scrolling in the window, and copying and pasting text. PuTTY can be downloaded from the given link. Let us summarize the topics covered in this lesson. Cassandra is a key-value NoSQL data store. Cassandra is a highly fault-tolerant database. Cassandra was started in 2008 at Facebook and became an Apache project in 2014. Cassandra supports tables, columns, and simple SQL statements. Cassandra provides fast reads and writes, thus supporting real-time data processing. Cassandra does not support aggregates or joins. If you need to work on an operating system other than Linux, you can access the software provided by VMware. PuTTY is a popular, free tool for connecting to Linux systems from Windows through a remote terminal. WinSCP is a popular tool for copying files between Windows and Linux. This demo will show the steps to install Ubuntu Virtual Machine, or VM, and connect with PuTTY. This demo will show the steps to install Ubuntu Virtual Machine, or VM, and connect with PuTTY. Download the VMware player from the given link and double-click the VM-player-7.1.0-249682.exe file to start the installation. The installation wizard appears with the welcome screen of the VMware player setup. Click the Next button to continue the installation process. In the License Agreement screen, select the I accept the terms in the license agreement radio button after reading the full agreement. Click the Next button to continue the installation process. In the Destination Folder screen, choose the default location and click the Next button to continue the installation process. In the Software Update screen, uncheck the Check for Product Updates on Startup checkbox. Click the Next button to continue. In the User Experience Improvement Program screen, uncheck the Help Improve VMware Player checkbox. Click the Next button to continue. In the Shortcuts screen, click the Next button to continue the installation process. In the Ready to Perform the Requested Operations screen, click the Continue button. The installation process will start. This will take a few minutes to complete. In the Setup Wizard Complete screen, click the Finish button to complete the installation. Start the VMware player. In the Welcome screen, click the Open a Virtual Machine option to open an existing VM. Download and unzip the Hadoop pseudoserver.rar file provided by Simplilearn. The extraction process begins. Open the VMware player again and click the Open a Virtual Machine option. Browse and double-click the unzipped Hadoop pseudoserver file. Note that the actual location may be different on your system. Open the Hadoop sudo distributed server.vmx file. Click the Take Ownership button. Click the Play Virtual Machine Play button to start the virtual machine. Click the I copied it button. In the Removable Devices pop-up window, select the Do Not Show This Hint Again checkbox and click the OK button. In the Software Updates window, click the Remind Me Later button to continue. When you get the login prompt, enter the login ID as Simplilearn and password as Simplilearn. Note that you can use Ctrl+Alt keys to switch between the VM screen and the Windows screen. After logging in, enter ifconfig in the command prompt to get the network configuration of the system. Write down the IP address of the system, as you will need it in the later part of the demo. Download PuTTY using the given link. Install and configure PuTTY to connect to the IP address saved earlier. Further, download WinSCP from the given link. WinSCP is a resourceful utility to exchange files between the Windows and Linux VM. You can install and configure WinSCP to connect to the IP address saved earlier. Run PuTTY by double-clicking the PuTTY-0.64-installer.exe file. In the Security Warning window, click the Run button. The Welcome Wizard appears. Click the Next button to continue. In the Select Destination Location window, click the Next button to continue. In the Select Start Menu folder window, click the Next button. In the Select Additional Tasks window, click the Next button to continue. Finally, in the Read to Install window, click the Install button. In the Setup wizard, uncheck the View README.txt checkbox and click the Finish button. Open PuTTY. In the PuTTY configuration window, enter the host name with the IP address saved in the earlier part of this demo. Simplilearn at the rate 192.168.189.128. Select Simplilearn from the given options and click the Load button. Ensure the IP address is 192.168.189.128. Next, click the Save button to save the settings and the Open button to open a connection to the VM. In the PuTTY Security Alert window, click the Yes button. In the Login prompt, enter the user ID as Simplilearn and the password as Simplilearn. Congratulations! You have successfully logged into the virtual machine from PuTTY. This VM will be used to set up Cassandra also in the later lessons. Note that multiple connections can be opened on the VM using PuTTY. This concludes the process of setting up and installing the VM. Let us summarize the topics covered in this lesson. Cassandra is a key-value NoSQL data store. Cassandra is a highly fault-tolerant database. Cassandra was started in 2008 at Facebook and became an Apache project in 2014. Cassandra supports tables, columns, and simple SQL statements. Cassandra provides fast reads and writes, thus supporting real-time data processing. Cassandra does not support aggregates or joins. If you need to work on an operating system other than Linux, you can access the software provided by VMware. PuTTY is a popular, free tool for connecting to Linux systems from Windows through a remote terminal. WinSCP is a popular tool for copying files between Windows and Linux. This concludes the lesson, Introduction to Cassandra. In the next lesson, we will introduce Cassandra Architecture. Hello, and welcome to the third lesson of the Apache Cassandra course offered by Simplilearn. This lesson will provide an overview of the Cassandra architecture. The Apache Cassandra course by Simplilearn is divided into 8 lessons as listed. This is the third lesson, Cassandra Architecture. After completing this lesson, you will be able to describe the Cassandra architecture, components of Cassandra, and the effects of Cassandra architecture. You will also be able to explain the partitioning of data in Cassandra, Cassandra topology, and various failure scenarios handled by Cassandra. Cassandra was designed to address many architecture requirements. The most important requirement is to ensure there is no single point of failure. This means that if there are 100 nodes in a cluster and a node fails, the cluster should continue to operate. This is in contrast to Hadoop, where the name node failure can cripple the entire system. Another requirement is to have massive scalability, so that a cluster can hold hundreds or thousands of nodes. It should be possible to add a new node to the cluster without stopping the cluster. Further, the architecture should be highly distributed, so that both processing and data can be distributed. Also, high performance of read and write of data is expected, so that the system can be used in real time. Cassandra is designed such that it has no master or slave nodes. It has a ring-type architecture. That is, its nodes are logically distributed like a ring. Data is automatically distributed across all the nodes. Similar to HDFS, data is replicated across the nodes for redundancy. Data is kept in memory and written to the disk in a lazy fashion. Hash values of the keys are used to distribute the data among nodes in the cluster. A hash value is a number that maps any given key to a numeric value. For example, the string ABC may be mapped to 101 and decimal number 25.34 may be mapped to 257. A hash value is generated using an algorithm so that the same value of the key always gives the same hash value. In a ring architecture, each node is assigned a token value. We will learn more about token values later in this lesson. Let us continue discussing the Cassandra architecture. Cassandra architecture supports multiple data centers. Data can be replicated across data centers. You can keep 3 copies of data in one data center and a 4th copy in a remote data center for remote backup. Data reads prefer a local data center to a remote data center. Cassandra architecture enables transparent distribution of data to nodes. This means you can determine the location of your data in the cluster based on the data. Any node can accept any request, as there are no masters or slaves. If a node has the data, it will return the data. Else it will send the request to the node that has the data. You can specify the number of replicas of the data to achieve the required level of redundancy. For example, if the data is very critical, you may want to specify a replication factor of 4 or 5. If the data is not critical, you may specify just 2. It also provides tunable consistency. That is, the level of consistency can be specified as a trade-off with performance. Transactions are always written to a commit log on disk so that they are durable. The Cassandra write process ensures fast writes. First, data is written to a commit log on disk. Then, the data is sent to a responsible node based on the hash value. Nodes write data to an in-memory table called memtable. From the memtable, data is written to an SS table in memory. SS table stands for sorted string table. This has a consolidated data of all of the updates to the table. From the SS table, data is updated to the actual table. If the responsible node is down, data will be written to another node identified as temp node. The temp node will hold the data temporarily till the responsible node comes alive. The diagram depicts the write process when data is written to Table A. Data is written to a commit log on disk for persistence. It is also written to an in-memory memtable. Memtable data is written to SS table, which is used to update the actual table. The term rack is usually used when explaining network topology. A rack is a group of machines housed in the same physical box. Each machine in the rack has its own CPU, memory, and hard disk. However, the rack has no CPU, memory, or hard disk of its own. All machines in the rack are connected to the network switch of the rack, and the rack's network switch is connected to the cluster. All machines on the rack have a common power supply. It is important to notice that a rack can fail due to two reasons: a network switch failure or a power supply failure. If a rack fails, none of the machines on the rack can be accessed. So it would seem as though all the nodes on the rack are down. The Cassandra read process ensures fast reads. Read happens across all nodes in parallel. If a node is down, data is read from the replica of the data. Priority for the replica is assigned on the basis of distance. Data on the same node is given first preference and is considered data local. Data on the same rack is given second preference and is considered rack local. Data on the same data center is given third preference and is considered data center local. Data in a different data center is given the least preference. Data in the mem table and SS table is checked first, so that the data can be retrieved faster if it is already in memory. The diagram represents a Cassandra cluster. It has two data centers, Data Center 1 and Data Center 2. Data Center 1 has 2 racks, while Data Center 2 has 3 racks. 15 nodes are distributed across this cluster, with nodes 1 to 4 on rack 1, nodes 5 to 7 on rack 2, and so on. The Cassandra read process is illustrated with an example on this screen. The diagram explains the Cassandra read process in a cluster with 2 data centers, 5 racks, and 15 nodes. Let us place data row 1 in this cluster. Data row 1 is a row of data with 4 replicas. The first copy is stored on node 3. The second copy is stored on node 5. And the third copy is stored on node 7. All these nodes are in Data Center 1. The fourth copy is stored on node 13 of Data Center 2. If a client process running on data node 7 wants to access data row 1, node 7 will be given the highest preference as the data is local here. The next preference is for node 5, where the data is rack local. The next preference is for node 3, where the data is on a different rack, but within the same data center. The least preference is given to node 13, that is in a different data center. So the read process preference in this example is node 7, node 5, node 3, and node 13 in that order. Cassandra performs transparent distribution of data by horizontally partitioning the data. A hash value is calculated based on the primary key of the data. The hash value of the key is mapped to a node in the cluster, and the first copy of the data is stored on that node. The distribution is transparent, as you can both calculate the hash value and determine where a particular row will be stored. The diagram on the screen depicts a 4-node cluster with token values of 0, 25, 50, and 75. For a given key, a hash value is generated in the range of 1 to 100. Keys with hash values in the range 1 to 25 are stored on the first node. 26 to 50 are stored on the second node. 51 to 75 are stored on the third node, and 76 to 100 are stored on the fourth node. Please note that actual tokens and hash values in Cassandra are 127-bit positive integers. Replication refers to the number of replicas that are maintained for each row. Replication provides redundancy of data for fault tolerance. A replication factor of 3 means that 3 copies of data are maintained in the system. In this case, even if 2 machines are down, you can access your data from the third copy. The default replication factor is 1. A replication factor of 1 means that a single copy of the data is maintained. So if the node that has the data fails, you will lose the data. Cassandra allows replication based on nodes, racks, and data centers, unlike HDFS, that allows replication based on only nodes and racks. Replication across data centers guarantees data availability even when a data center is down. Network topology refers to how the nodes, racks, and data centers in a cluster are organized. You can specify a network topology for your cluster in the Cassandra-topology.properties file. Your data centers and racks can be specified for each node in the cluster. The format is a list of lines, with each line specifying the IP address. For unknown nodes, a default can be specified. You can also specify the host name of the node instead of an IP address. The diagram depicts an example of a topology configuration file. This file shows the topology defined for 4 nodes. The node with IP address 192.168.1.100 is mapped to data center DC1 and is present on the rack RAC1. The node with IP address 192.168.2.200 is mapped to data center DC2 and is present on the rack RAC2. Similarly, the node with IP address 10.20.114.10 is mapped to data center DC2 and rack RAC1, and the node with IP address 10.20.114.11 is mapped to data center DC2 and rack RAC1. There is also a default assignment of data center DC1 and rack RAC1 so that any unassigned nodes will get this data center and rack. Snitches define topology in Cassandra. A snitch defines a group of nodes into racks and data centers. 2 types of snitches are most popular: a simple snitch and a property file snitch. A simple snitch is used for single data centers with no racks. A property file snitch is used for multiple data centers with multiple racks. Replication in Cassandra is based on the snitches. Cassandra uses a Gossia Protocol to communicate with nodes in a cluster. It is an inter-node communication mechanism similar to the Heartbeat Protocol in Hadoop. Cassandra uses the Gossia Protocol to discover the location of other nodes in the cluster and get state information of other nodes in the cluster. The gossip process runs periodically on each node and exchanges state information with 3 other nodes in the cluster. Eventually, information is propagated to all cluster nodes. Even if there are 1,000 nodes, information is propagated to all the nodes within a few seconds. The image depicts the Gossia Protocol process. In Step 1, one node connects to 3 other nodes. In Step 2, each of the 3 nodes connects to 3 other nodes, thus connecting to 9 nodes in total in Step 2. So a total of 13 nodes are connected in 2 steps. Seed nodes are used to bootstrap the Gossia protocol. They are specified in the configuration file cassandra.yaml. Seed nodes are used for bootstrapping the Gossia protocol when a node is started or restarted. They are used to achieve a steady state where each node is connected to every other node, but are not required during the steady state. The diagram depicts a startup of a cluster with 2 seed nodes. Initially, there is no connection between the nodes. On startup, 2 nodes connect to 2 other nodes that are specified as seed nodes. Once all the 4 nodes are connected, seed node information is no longer required as steady state is achieved. The main configuration file in Cassandra is the cassandra.yaml file. We will look at this file in more detail in the lesson on installation. Right now, just remember that this file contains the name of the cluster, seed nodes for this node, topology file information, and data file location. This file is located in /etc/Cassandra in some installations, and in /etc/Cassandra/conf directory in others. Virtual nodes in a Cassandra cluster are also called vnodes. Vnodes can be defined for each physical node in the cluster. Each node in the ring can hold multiple virtual nodes. By default, each node has 256 virtual nodes. Virtual nodes help achieve finer granularity in the partitioning of data, and data gets partitioned into each virtual node using the hash value of the key. On adding a new node to the cluster, the virtual nodes on it get equal portions of the existing data, so there is no need to separately balance the data by running a balancer. The image depicts a cluster with 4 physical nodes. Each physical node in the cluster has 4 virtual nodes, so there are 16 vnodes in the cluster. If 32 terabyte of data is stored on the cluster, each vnode will get 2 terabyte of data to store. If another physical node with 4 virtual nodes is added to the cluster, the data will be distributed to 20 vnodes in total, such that each vnode will now have 1.6 terabyte of data. The token generator is used in Cassandra versions earlier than version 1.2 to assign a token to each node in the cluster. In these versions, there was no concept of virtual nodes, and only physical nodes were considered for distribution of data. The token generator tool is used to generate a token for each node in the cluster based on the data centers and number of nodes in each data center. A token in Cassandra is a 127-bit integer assigned to a node. Data partitioning is done based on the token of the nodes as described earlier in this lesson. Starting from version 1.2 of Cassandra, vnodes are also assigned tokens, and this assignment is done automatically so that the use of the token generator tool is not required. The token generator is an interactive tool which generates tokens for the topology specified. Let us now look at an example in which the token generator is run for a cluster with 2 data centers. Type token-generator on the command line to run the tool. A question is asked next. How many data centers will participate in this cluster? In the example, specify 2 as the number of data centers and press Enter. Next, the question, how many nodes are in data center number 1 is asked. Type 5 and press Enter. The next question is, how many nodes are in data center number 2? Type 4 and press Enter. The tokens are calculated and displayed on screen. The example shows the token numbers being generated for 5 nodes in Data Center 1 and 4 nodes in Data Center 2. The first node always has the token value as 0. These token numbers will be copied to the Cassandra.yaml configuration file for each node. Cassandra is highly fault-tolerant. If a node fails, other nodes detect the node failure. Request for data on that node is routed to other nodes that have the replica of that data. Writes are handled by a temporary node till the node is restarted. Any mem table or SS table data that is lost is recovered from commit log. A node can be permanently removed using the Node Tool utility. When a disk becomes corrupt, Cassandra detects the problem and takes corrective action. The data on the disk becomes inaccessible, and read of data from the node is not possible. This issue will be treated like node failure for that portion of data. Mem table and SS table will not be affected as they are in-memory tables. Commit log has replicas, and they will be used for recovery. Sometimes a rack could stop functioning due to power failure or a network switch problem. As a consequence, all the nodes on the rack become inaccessible. Read of data from the rack nodes is not possible. The reads will be routed to other replicas of the data. This will be treated as if each node in the rack has failed. Data center failure occurs when a data center is shut down for maintenance or when it fails due to natural calamities. When that happens, all data in the data center will become inaccessible. All reads have to be routed to other data centers, and the replica copies in other data centers will be used. Though the system will be operational, clients may notice slowdown due to network latency. This is because multiple data centers are normally located at physically different locations and connected by a wide area network. Let us summarize the topics covered in this lesson. Cassandra has a ring-type architecture. Cassandra has no master nodes and no single point of failure. Cassandra supports network topology with multiple data centers, multiple racks, and nodes. Cassandra read and write processes ensure fast read and write of data. Cassandra partitions the data in a transparent way by using the hash value of keys. Replication in Cassandra can be done across data centers. Cassandra uses the Gossia Protocol for internode communication. Cassandra can handle node, disk, rack, or data center failures. This concludes the lesson, Cassandra Architecture.